Here are solutions to homework set number 3 for ECE 321. Now this homework set looks at filters. How to design a filter using an op-amp circuit. The first problem looks at if I have a transfer function. This is oftentimes how filters are written. I have an input, an output, and a gain that gains my filter. This represents a differential equation. If I cross multiply and factor it out, I have s squared plus 15s plus 50 times y is 80 times x. The plus operator s means derivative, so this is the second derivative of y plus 15 times the first derivative plus 50 times y is 80 times x. So this differential equation is the same as that transfer function. The reason we do that is it makes analysis of differential equations much easier. If I have the following function, I can use superposition. What superposition does is it says that if I have a function f of a plus b that's equal to f of a plus f of b, treat this as two separate problems. I have a DC input, 6, and a sine wave input. For the DC input, s equals 0, everything's e to the st. When s equals 0, I have e to the 0 or 1, so that's 6 times 1, s equals 0. The mathematical representation for 6 is 6. This is the gain everywhere. All I care about is what's the gain at s equals 0 times the input at s equals 0. And the answer is 9.6. The second part, when x is 2 cosine 4t plus 3 sine of 4t, now s is j4. X is 2 minus j3. Real part's cosine minus j is sine. The output then, this is the gain everywhere. All I care about what's the gain at 4 radians per second, the frequency of the input, times the input at 4 radians per second. Multiply it all out, I get a complex number. Real part means cosine minus j is sine. The total answer then is DC plus AC. I add the DC term plus the AC term. That's what phasors do for you. I can solve a differential equation with sine wave inputs. That's filter analysis. Given a filter, I can build an op-amp circuit to implement it. And this is kind of like a Lego building blocks. It depends upon the poles, what circuit you use. If I have real poles, I can use this circuit. I've got the resistors going up by 10 times, so approximately, these are 3 separate RC filters. This one, I want to have 1 over RC is 2. Here, 1 over RC is 8. Here, 1 over RC is 10. Given R, solve for C. This has the DC gain of 1. My plant has the DC gain of 2.5. So add a gain of 2.5 at the end, and I have the same filter. This is one way to do it, and there's others. Problem 3 is, what if you have complex poles? Here, polar form works a little bit better. I've got one pole at 4.4 at 83 degrees. The other one is 5.4 at 64 degrees. So I'm going to use this circuit, different building block. On this one, 1 over RC is your first pole. That's 4.47. So that's equal to 4.47. To get the angle, that comes from here. To find k, that's 1 plus the ratio. It's 3 minus k is 2 times the cosine of the angle. The angle I want is 83 degrees. Gives me k is 2.77. So k is 1 plus the ratio. And this is a non-inverting amplifier. The gain of a non-inverting amplifier is 1 plus the resistor ratio. I want the gain to be 2.77, so pick this to be 1.77 to 1. That's stage 1. The second stage, I want 1 over RC to be 5.44. Given R, solve for C. To solve for K, again 3 minus K is 2 times cosine of the angle. Solve for K. K is 2.14. That's 1 plus the resistor ratio. Make that 1.14 times 100K. So there's my circuit. The DC gains off a little bit. The DC gain is supposed to be 0.3333. That's take your system, plug in s equals 0. That's the actual DC gain, but it should be. My circuit has a DC gain of 2.77 times 2.14. So the gain is off a little bit. What that means is my output isn't just y, it's actually 17.9 times y. That's kind of how I prefer doing it. You're going to need a gain anyway, typically in amplifiers. This provides a gain of 17 free of charge. Live with it and adjust for the gain elsewhere. Problem 4. Given the gain versus frequency, find the filter. Well, here, I know I've got a resonance right here, so I know I have 3 poles. One has a complex part at 4 radians per second, one has a complex pole at 11 radians per second, one has a complex pole at 16 radians per second. The bandwidth tells you the real part. This bandwidth is about 0.5, so half of that is the real part. This has a bandwidth of about 1, so the real part's about 0.5. This has a bandwidth of about 0.5, half of that is the real part. So there's my poles, plus the DC gain of 0, that gives me a 0 at s equals 0. I can check, here's the poles, calculate the gain versus frequency, find the maximum, add a gain k so that the maximum is 1. Kind of match up this curve. And here's what I get. This is a little bit off. I want to bring that down a little bit, and I could do that by adjusting the real part. I've got a pole at J4. As I move it closer to the j omega axis, this gets bigger and bigger. If it's too big, I'll move it away from the j omega axis. That'll bring that point down. But it's kind of got the right shape. The last problem is filter design. Come up with a filter with the following gain versus frequency. This is where fminsearch is really useful. I'm going to guess the form of the filter. I'm going to have 5 poles and a gain on top. Pick those numbers to give you that gain versus frequency. So what I'm going to do is use fminsearch. I'm going to guess A, B, C, D, E, F, and it'll do something. My function then will take the difference between the two, add up the sum squared difference, sum squared error, and return that. What filter, what A, B, C, D, E, F minimize the sum squared error? That's a problem for fminsearch. So here's my cost function. I'm going to guess z. Parsing it, z means A, B, C, D, E, F. Here's the filter that I want. And one trick, I offset this just a little bit. That way I don't have to worry about greater than equals, because it's never going to be equal. Here's the actual filter. Here's the difference. Have j return the sum squared error, and just for fun, plot the two. As I run it, well, if this is my first guess, here's my filter, here's what it should be. That's not a very good guess. The sum squared difference between the two is fairly large. Can I do better? Well, if I go to fminsearch and say, now optimize this filter, here's my first guess, it'll iterate, and the best I could do is sum squared error of 2. Trying it again, just to make sure it converges, same answer. That must be the best it could do. And if you look at the gain versus frequency, it's actually not too bad. That's the beauty of fminsearch. Knowing nothing about filter design, I can do a pretty good job designing filters. So that's homework set number 3 for ECE 321 Analog Electronics for spring 2023.